talk a little bit about why I got interested in this stuff in the first place. So if anybody knows who this is, I'm really excited about it. We can talk later. For those that don't know who this is Sydney Bristow from the television show Alias, which aired in about 2001. It's over now, but I was pretty obsessed with it at the time. So when I went to go register for classes my freshman year, I was thinking a lot about Alias. I was thinking about this character, Sydney Bristow, who was a double agent for the CIA, got to dress up in cool costumes and do like spy stuff all around the world. It was very fascinating. And so when I was registering for classes, I saw this class called Introduction to Cryptology, and I signed up right away. I was really excited. I thought I was going to be exactly like Sydney Bristow and go work for the State Department or something cool like that. What ended up happening is I learned a lot of math theory and number theory and did a lot of math proofs. It wasn't exactly my ideal situation. I wasn't learning how to break codes. Unfortunately, I didn't learn how to be a spy. I did get really good at math proofs for like a semester, and of course have since forgotten all of that. But I wanted to spend some time talking about the practical considerations of cryptology and cryptography because there is practical considerations beyond code breaking. Cryptography is the underlying foundation for a lot of the things we use online for authentication now, which is something that I work a lot on. And in all likelihood, a lot of you aren't going to go on to build new cryptographic systems for the stuff that you're working on. But I do think that it's good to know the underlying principles and how you're going to be dealing with them in the systems that you interact with every day. So this talk is going to be a refresher if you ever took a cryptography class before, but refreshers can be really useful. And, if this is not something that you've done a lot of in the past, this will be a pretty good overview of what public key cryptography is and where you can use it in the real world. So my name is Kelly Robinson. I am recording this from Brooklyn, New York. I hope you are having a good day wherever you may be, sheltering in place still and avoiding people. I have been working at Twilio for about 3 years now, and I specifically work on Twilio's account security products, and so that's things like two-factor authentication, phone verification, phone intelligence, anything that has to do with securing our customers and users. And this team has evolved a lot since we acquired Authy, which was almost 5 years ago, or actually over 5 years ago now. Authy is our free consumer application for two-factor authentication. And like I mentioned, a lot of authentication uses cryptography under the hood, and that includes Authy. And so this is some research that I had done just to kind of both better understand it myself, but also be able to understand how and be able to better explain how our applications work to the customers and people that we're dealing with. So all stories with cryptography have to do with this cast of characters called Alice and Bob. This is something that you'll see in a lot of anecdotes that are explaining cryptography, so I didn't want to stray too far from that here, though our Alice and Bob here are being played by Regina and Gretchen. Alice and Bob, of course, have a history of illicit dealings. We don't really know what they're up to, but they don't want us or the ever-curious Eve to find out. So Alice and Bob could pass secret messages to each other by encrypting the text using some kind of agreed upon cipher. Maybe that's through like substituting letters for other letters, substituting letters for numbers, shifting letters in one direction or another. They could use any kind of method that they had agreed upon, but they both agree on this in advance so they know how to encode and decode the messages when they end up with a message from the other person. So if you ever pass notes in school and your friends, came up with a secret plan for how to do this in case the teacher, confiscated something, the idea is the same there. You might have had a secret code in order to protect this from people that you didn't want to read the messages that you were sending. And so this is known as symmetric key cryptography. The same key is used in both directions, and it worked really well for World War II spies and high school kids. But what happens when our secret messengers can't agree on the key in advance? And this is a very common thing that happens today where you're not talking to somebody in person, you're dealing with an entity on one end or the other that might be a computer, not another person. So this is why we invented public key or asymmetric cryptography, so that two people like Alice and Bob could communicate securely without having to meet first and agree on a shared encryption key. And they also don't have to risk that an eavesdropper like Eve would intercept the key over an unsecured communication channel when they're trying to agree on that cipher in the first place. And so public key cryptography is a really necessary advancement because of the internet. We're no longer only transacting and communicating with people that we know and trust. And so what is public key cryptography? I specifically say entity here because this is used in a lot of ways. Like I said, you might be dealing with a computer on one end of the spectrum, and so it's not just going to be between two people. One or both sides could be that computer. And so in public key cryptography or asymmetric cryptography, there is going to be two keys involved. One is public. This can be shared. You don't have to be worried about this one leaking. And then there's also always going to be a private key that is one that you want to keep secret, that you don't want to ever leak to somebody else other than yourself, or usually the device which you generate that key on. And so these keys are generated at the same time using an algorithm, and they're mathematically linked. And so you can see in this diagram here, there's two different keys. There's a public key represented in blue there, and a private key that's represented in green. And so Alice is sending a message to Bob. And so when Alice wants to encrypt the message, she uses Bob's public key. And so Bob has published his public key so that Alice can use, or anyone can use, the public key to encrypt a message. That creates a ciphertext. And because Bob is the only one that has this linked private key, when Bob uses the private key to decode the message, that means that he's the only one that's able to actually decode the message. And so then Bob can end up with the original text that Alice was trying to send. Just for the purposes of this conversation here, when I say asymmetric key cryptography or public key cryptography or PKC, these are all talking about the same things. And I also wanted to kind of clarify that for most of this explanation, I'm going to talk about how these keys are generated. I'm going to be using the RSA algorithm. There are other algorithms, kind of like I mentioned here. I do get into those a little bit just to introduce some other things that are going on. But RSA is a really common algorithm that a lot of systems are still using. And so what do we talk about when we talk about public key cryptography? And so there's two use cases with RSA here and use cases for encrypting and decrypting messages. And so the first there is, like I said, encrypting with the public key. This is the example that we kind of already walked through. And so this is where you would want to send messages that you don't want anyone else to read besides the intended recipient. And the second use case there is signing a message with your private key. And the use case here is really useful for things like authentication, where you want to verify that you are the one that sent the message or took the action of some kind. You are the only one with a private key, and so if somebody is able to decrypt that with the public key, they can trust that you were the one that initiated the message. And these methods can be combined to both encrypt and sign a message with two different key pairs. And so again, this is what we already saw, encrypting with a public key. The use case here is sending a message that you don't want anyone else to read. And so this is how you would encrypt a message that only Bob can decode with his private key. On the flip side, if you wanted to sign a message with your private key, and again, this is the use case where you're verifying that you are the one that sent the message. Again, useful for authentication context here. And so in this case, Alice would encrypt a message with her private key and then send the message to Bob or a computer or someone else. And then Bob can decrypt the message with the public key, compare that to the original message and say, hey, I got the same thing on the other side here. This is proof that Alice is the one that sent the message, since the public key can be used to decrypt messages, can only be used to decrypt messages that were signed with Alice's private key. The short explanation for how keys are generated is math. I'm actually going to walk through a small example of the principles behind RSA and how it works, though. And to do this, I wanted to introduce one of the concepts for the RSA algorithm by thinking about mixing together two paint colors. And this is important because if you think about mixing together two paint colors, it's really simple to combine paint colors. But once you have that mix, it's really complicated to back that out into the original colors there. Even if you know that yellow and blue create green, you might not know exactly which shades of yellow and blue were used to create green. You might be able to recreate this by testing a bunch of different paint colors. But that's going to take you a really long time, and it's not exactly a really efficient way to back this out. And so we see this kind of one-way function, this one-way example that's really easy to do in one way and really hard to undo in the other direction. We see this all the time in things like physical security. And so you can think about things like locks and tamper-proof screws, sealed packages, zip ties, these types of things that are really easy to, lock in one direction, but really hard to undo unless you either have a key, you might be able to undo it, but not easily without detection. It might take you a lot of time or money. It's difficult that most people aren't going to take the time or money to try. It's not that these things can't be undone, but it's just hard enough that it's going to not make it worth it for a lot of potential attackers. And so cryptography relies on the same principle, using calculations that are easy to do in one direction and really hard to reverse unless you have a key. And so we call these trapdoor one-way functions. And one way we can achieve this in digital security is using really large prime numbers and multiplying them together. So it's easy for a computer to compute the product of two 600-digit prime numbers, but it's actually really hard for a computer to take the result and find its factors. And trapdoor functions are a type of one-way function, but there is an out there. That's the trapdoor part. There's a key. And in this case, the key would be having one of those factors. So there's a few ways to do this, including thinking about how to undo a trapdoor function. You can think about which is easier here, finding the two prime factors of 4,757. You could brute force trial and error this. For a 4-digit number like this, you could write a script that loops through known prime numbers. I think we know all the prime numbers, or I know we know all the prime numbers up through 4,757. But once that target number becomes like 1,000 digits long, that's going to take a computer a really long time and a lot of processing power in order to be able to get those prime factors. But then if you think about what is the result if I multiply 67 and 71, that's really easy, right? Like you can all do that using a simple calculator. And so that's an example of how these one-way functions work. And so let's walk through a very, very basic example of how to generate a key pair using the RSA algorithm. And there's actually code for doing this on my GitHub if you want to play around with this and work through a real example. So we have to choose some inputs. P and Q are the primes. And again, like in real life, these would be very, very, very large numbers, but we're going to make those 67 and 71. E is what's called the public exponent. And then we do some calculations. And these are all trapdoor functions, right? So we're multiplying together the two prime numbers. We're multiplying together, take one off of each one of those and multiply them together. We're using the modular multiplicative inverse of some of these numbers that have been calculated. And we use these numbers to create our public and our private keys. And that's when we get these keys back, and then we can use the private key and the public key to both encrypt and decrypt the message. And then once we both encrypt and decrypt the message, we're left with the same result of the original message. And that's pretty cool. So there are a few other common algorithms out there. One that we see often is the Diffie-Hellman key exchange. And this is a little bit different from the public key generation that we saw previously, in that we're building a shared secret together. And so we start with a common seed, or in this example, we're using paint again to kind of illustrate how this works. You each mix in your private key or your secret paint color in that. And then you end up with this result of mixing those two together, the product of your secret and the public key, and then you can exchange this second public key, and then once you mix back in your private in a predictable way, you end up with a shared secret at the end. This is a little bit slow to do initially, but then once you have built that shared secret, it's actually really efficient, because then you can use the symmetric key cryptography as the result of this, because you have that shared secret that you can use in either direction. Another thing that you might encounter is elliptic curve cryptography. And this is where you would have some kind of elliptic curve equation, and the one-way function here is bouncing around this curve to different points on the curve in a predictable way some different number of times. And you end up with a point on the curve that is your secret key. And it's similar to how the modular arithmetic works in RSA or Diffie-Hellman. This is actually what Bitcoin uses. And ECC is what a lot of things are moving towards. It's not as widely implemented yet because it's still newer and somewhat harder to implement, but it's still a lot more efficient. It's actually a lot more efficient, and I'm going to talk a little bit about why that is. And to talk about efficiency, we have to talk about key size, because key size affects how secure the algorithm that we're using actually is. And so in this example from XKCD, we're using a key size of 4096. The reason this is funny is because that's actually a really big key size for RSA. And so the joke here is that like you're using this really secure RSA key size, you're securing your laptop on top of it. Of course, you know, any attacker can just hit you with a wrench and get you to tell them your password. But key sizes in different algorithms produce different security strengths. And so here you can see that a much smaller ECC key size is just as secure as a large RSA key size. And so security strength is measured in bits of security. And so this is kind of a facsimile of how we want to evaluate how secure an algorithm is. And so NIST, or the National Institute of Technology, estimates that 112 bits of security is good for now. So actually 2048-bit RSA key is the recommendation currently. And their last I checked, their conservative estimate was that by 2030, we need to increase the requirement to 128 bits of security. And that's due to advancements in hardware and computation power. And so a lot of companies, if they're looking at this, they're, you know, getting ahead of the curve and they're being conservative around how much security they need. And so that in case these systems are in place for more than 10 years, they're still going to be secure at that time. Security strength is a measure of how much work it would take to crack the algorithm. And so that's kind of why it's used as a good measure in order to understand how effective different key sizes are with different algorithms. I do want to take a minute to kind of talk about how you could implement this in a programming language. This is going to be looking at how you use public key cryptography in Python. One of the things that I like about this library, the cryptography library in Python, is that it breaks things up into safe and dangerous sections. And so you can see here that this has like a hazmat section that kind of indicates that you might be entering a dangerous zone. The inputs here include the exponent and the key size. The public exponent is usually 65,537. I don't know why exactly we settled on that number. If anybody does, they can feel free to let me know. But it's baked into a lot of systems now. Key size here, you can use 2048. This is their nice warning in the hazmat section that you should only use this if you know what you're doing, because there's landmines, dragons, and dinosaurs with laser guns. All right. But using this Python library, once you generate the private key, the public key is included in the object there. And so you can get the public key out of the private key. Again, those are always going to be linked. The ciphertext is what is the result of encrypting a message with your public key. And then you can use that private key to decrypt the message. Compare those. You end up with the same result. Similarly, if you're using this to sign a message, you can sign the message with your private key. And then in the very Pythonic way, if you try to verify that the signature matches the original message using the public key, it's going to throw an exception. And so important thing to note here is that in the practical implementations of this, not only are you signing a message with your private key, but then when you go to verify, you do have to include the original message or some kind of information from the original message to know that saying, hey, what you end up decrypting this with my public key needs to match the original thing that I sent. And so there are a lot of everyday uses of public key cryptography, so TLS, so everything that's baked into securing websites, communications with websites, so anything that's HTTPS is using some cryptography there. Of course, Bitcoin, everyone's favorite. Authy, like I mentioned, uses this under the hood. SSH, if you're doing a secure connection into a server, that's going to use it. And then there's specific types of JSON web tokens, depending on how you are encoding those, that are going to also use public key cryptography. The example that I like to use is the push authentication that we use with Authy and Verify, the APIs that we have at Twilio. And so this is a really kind of like easy example to illustrate this. And one of the other reasons that this is a more secure form of two-factor authentication. And so for every site that you enable on Authy, your device actually generates a new RSA key pair on your device. And then it only sends the public key to the Authy servers. And so that makes it a little bit more secure. And this is also similar to how biometric authentication works on your phone. You're not actually ever you're not storing like your Face ID or your fingerprint on a lot of your phones. That information is only ever stored on the device. And so the private information never leaves the device, and that's what helps keep it more secure, and also gives it a specific fingerprint, for better words, of the device that you're using. You couldn't be authenticating from a different device using the same key pair that was generated on your original phone. So like I said, the private key never leaves your device. And then when you approve or deny a request on your device, the Authy app will validate that the request came from the sender who is in control of the private key. And it's also going to validate that the authorization request has not been modified in transit. Another example of using this in the wild is generating an SSH key. And this is something that a lot of people have probably done with something like GitHub. And so you might have forgotten about this if you haven't gotten a new computer in a while. But every time you get a new computer, what you're going to have to do, or if you accidentally delete this or something like this, you need to generate a new key pair on your device. And GitHub has good documentation for how to do this. And you can see some information about how they're telling you to generate this key pair. And so using the SSH keygen function, so this is built into macOS computers. So you specify the algorithm, you specify the key size. Again, GitHub is telling you to use a pretty large key size here, and then you're giving some information about who you are. And so actually, just to go back to this for a minute, what ends up happening there is then the key size, or the key pair rather, that you generate after this, what GitHub tells you to do is say, hey, this key pair, you have the private key on your device. This is in your computer. It's stored in your computer in an SSH key pair file or key file. And then you copy the public key and add that to something like GitHub. And so when GitHub has that public key on their servers, that's how they can verify that you are the one pushing commits to your account. And so the best applications of this kinds of concepts are when the end user doesn't actually have to think about it. And so things like PGP have gotten mocked a lot for being hard to use. Like, you don't actually know if somebody says, here's my PGP key, like, signed message, like, am I actually going to go through the process of verifying this? I don't know. So this is something that if, you want to be extra safe, you can check that there's a big block of jumbled letters at the bottom of the, that's just the XKCD joke. But because these things are hard, you want to be careful about implementing cryptography in your applications. There's constant warning not to roll your own crypto. If you're somebody that is in implementing cryptographic systems at your company, a lot of times you have a lot of experience doing this and probably degrees in this kind of stuff. I certainly wouldn't trust myself to implement cryptographic systems because, for the types of real world applications that we're using them for, there's libraries that exist for this kind of stuff. Like if you're doing something that requires crypto, like JSON web tokens, TLS, login, there's solutions out there that implement a lot of this stuff for you so that you don't have to think about what's going on under the hood. So this is a lot of information. If you do want more references, I compiled a lot of what is in this presentation into a blog post that has a lot of links to other great resources to learn more about cryptography if you want to learn more. If you want some further listening, everybody loves a good podcast these days. This is actually a really fascinating story. In 1940s Australia, there was an unidentified man that was found dead on the beach. And this story has everything. It's got unsolved murder, it's got illicit affairs, it's got Russian spy theories. But part of the remaining mystery here is that there was a piece of paper that was found in the dead man's pocket that contains some kind of ciphertext. And to this day, that ciphertext has not been decrypted. So now that you are all cryptography experts, I challenge you to go solve this puzzle. I hope that this has given you a good overview of, or a good refresher on some of the things behind public key cryptography. Once again, my name is Kelly Robinson, and thank you for listening.